I'm a senior engineer at Power Tech Labs, and I'm a member of the Canada NGN group. I see that most people are muted themselves. That's great. To just avoid noises, I ask everyone to please, if not, like mute yourself and turn off your cameras. Maybe like it would also help with the speed of internet and all that. Also, if you have any questions throughout the conference or this webinar, you can post your questions in the chat section, and then we can address them at the Q&A section at the end of the webinar. And if we don't answer all the questions, we can basically post the answers later on, so we have a copy of that. So a little bit of background about SIGRE Canada NGN. It was formed in 2019. Our mission is to support the next generation of Canadian power system professionals by providing opportunities for technical growth, networking, and leadership skills, mainly for students and young members. So far, we had several events, such as the NGN Forum in Montreal last year, social events, and webinars. This is our, I guess, first technical webinar in this year. There's also several opportunities to win awards and basically expand your networks. I encourage everyone to go to our SIGRE website, which is essentially sigre-canada.org/next generation network. You can just Google it and you'll find it. Also, we have a LinkedIn page that you can find a lot of information and keep up to date. There are a few awards that we give out every year or every other year. It's called, there's like the list a few of them. There's Young Member Best Paper Award, there's a Student Best Paper Award, there is SIGRE Paris sponsorship, there is Young Member Showcase presentation, and much more. So I encourage everyone to join our LinkedIn page and follow up, and you can also see the lists of all the executive members, and you can definitely reach out to any of us if you have any questions and you want to know more. Okay, so with that, so let's just move on to our webinar, which is titled Managing the Impact of Weather and Power System Assets. It's presented by Alexandra Modelewska. She is the Business Development Executive for Transmission and Distribution at Digital Engineering. She is responsible for helping utility representatives boost performance, optimize maintenance, improve safety, reduce consumer downtime, and add value through a selection of tried and tested innovative services. She completed her studies at McGill University in Canada, and prior to joining digital engineering, she spent several years at CID International, leading numerous T&D groups. She's one of our founding members of SIGRE Canada's NGN and an advisory committee member of Women in Renewable Energy. Okay, without any further ado, Alex, the floor is yours.
Thank you, Farhad. And welcome everybody to SIGRE Canada NGN's first technical webinar. I hope everybody's staying safe during this unprecedented time. And yeah, I thank you all for joining the webinar today. Like Farhad said, if there are any questions, please feel free to ask them using the chat function. If we don't get to your questions today, I can always respond and send them over. Excellent. So as Farhad mentioned, my name is Alex Modelewska, and I'm representing digital engineering, which is based in Bristol, UK. I hope that I can provide an insight into the many different ways that the weather can affect power systems and how it can be used to make informed decisions. In today's presentation, I will briefly introduce digital engineering, then discuss the weather in general, and then why it is important to power system assets. I will then go on to discuss weather modeling and how they can be validated. And finally, I will run through a selection of case studies for projects that have used weather model data to help clients manage the impacts of weather on their assets. So to start off, digital engineering was formed in 2010, and so we now have a decade of experience in a range of different disciplines. Our team is passionate about weather simulations, engineering modeling, and data analytics. The wide skills base represented at digital engineering allows us to solve problems creatively, improving on existing solutions in new and innovative ways. We've worked with numerous utilities, some of which are listed here, include National Grid, Scottish Power, FortisBC. We also provide regular forecasts of renewable power generation to Bloomberg for several countries in Europe. So now I will discuss the weather. So why is the weather important to power systems and how we can measure the weather and model it? So the weather is an important consideration for managing power system assets, particularly since a lot of those assets are located outside. Demand, supply, operations, maintenance, and design are all affected by the weather. Electricity demand increases when the weather is cold and people turn on their heating and lights. Electricity demand reduces during warm and sunny periods. Although when it gets quite hot, air conditioning becomes another variable to be considered. An increasing amount of electricity is produced by wind and solar generators, meaning that electricity supply is more dependent on the weather than ever before. System operation is consequently affected by the weather due to supply and demand fluctuations. And maintenance is affected by the weather, as engineers may not be able to inspect or maintain assets during adverse weather conditions. And certain weather effects can also age assets a lot faster than without those weather conditions. The design of assets depends on the weather. For example, overhead line designs must be able to withstand extreme wind and ice loads in particular regions. But if you want to manage the impact of the weather, you need to be able to measure it. There are two main ways to understand the weather: to measure it directly or to use a weather prediction model. There are also a number of pros and cons for each option, and we'll go through these for both. So the pros of a MET station, or meteorological station. A weather station reports real measured data, which can be considered highly accurate as long as the equipment has been calibrated correctly. A weather station can be installed at the precise location of interest, for example, at a single overhead line tower. There are publicly available weather station data sets, which are extremely useful, some of which have been reliably collecting data for decades. The cons are that a weather station only provides data within a certain radius. So a MET station is generally only useful for a handful of overhead line towers nearby. They are also expensive to install. Once a station has been installed, it can only collect data from that point onward. It won't be able to provide historical conditions. Instrumentation changes can affect the consistency of weather records, and decisions made about where to install a MET station can affect how useful the data is. For example, a station installed within a forested area will not provide weather data that is representative of a nearby location in an open field, and vice versa. I provided a visual example in this image. A meteorological mast was installed around 1/3 of the way up this tower. So that's below the tops of the surrounding trees. And these trees created a wind barrier, significantly impacting wind speed and direction measurements. So this meant that the measurement data was not representative of a location only a handful of meters away. This is a very good example of kind of how you need to be careful when you're using weather station data. So the alternative to a MET mast is to use a weather model. So there are also pros and cons to using weather models. There's a large amount of historical weather data available globally. The data can be accurate, again, depending on calibration, and weather modeling can be a significantly cheaper option than installing a network of weather stations. The cons are that the technology is relatively new and therefore isn't widely adopted or considered in engineering design standards. And there are often questions over the accuracy of the models. And so I will try to address some of these concerns in the following slides. So now that we have established that weather models are an alternative to weather stations, I will provide some background on numerical weather prediction models. And we'll look at everything from large-scale global models to more detailed regional models. So to set the scene, numerical weather prediction has become a practical solution due to increases in computing power over the last decade or so. The image on the right here is an illustration of Moore's law, which states that computing power has approximately doubled every 2 years. So this allows models to be run at higher resolution and with more detailed physical modeling approaches. The reduction in costs also opens up weather modeling to more businesses, who are now able to simulate decades of historical weather data with these models. What small businesses don't tend to do is model the weather on a global scale. There are a range of large organizations, such as Environment Canada or NASA, that run global weather models, and I've listed a handful here. The data provided by these large-scale organizations may or may not be publicly available, but it is extremely useful. And so a lot of smaller organizations or smaller companies use data directly from these organizations within their projects, or use the data as inputs to smaller regional weather models, which I will discuss in a moment. Global weather models combine physical models with real weather records to ensure these models are as accurate as possible. So this process is known as assimilation. This includes data from a range of sources, including satellites, ground-based observation stations, and ships and aircraft. The global models are typically at their most accurate from the 1980s onwards because of the technology that was available back then, and then that was not available before then, resulting in decades of consistent weather data. Global weather models are run at a low resolution due to the huge computing requirement for a global model. And what we do is take global weather model data and use this as an input into regional models. So these models include a smaller area at a higher resolution, which makes the data much more useful for power system applications. The images on the right-hand side here show the progression from global weather data to regional data. So the first image shows a map of rainfall at the kind of resolution that is typical of a global model, so around 30 to 50 kilometers. You may also be able to see the dots that illustrate the weather stations over the area. The global model may predict the same weather from multiple weather stations. The next two images show the progression to more detailed models. We use global weather data as those inputs into these models that cover the smaller areas. So as the level of detail goes up, the variations in rainfall over this area are much better captured and line up with the readings from the weather stations. So this process is typically referred to as downscaling. And so you can see that if you actually zoom in on the weather, you can see that, for example, these three stations that on the global weather model appear to be experiencing the exact same precipitation are actually experiencing completely different precipitation. And so that's why extremely detailed weather data is vital to many applications. There are other methods available to increase this resolution even further. So some examples are large eddy simulations and computational fluid dynamics. Computational fluid dynamics, or CFD, it can model the impact of individual buildings and trees. However, these dynamic models are extremely expensive, or they tend to be quite expensive. A cheaper alternative to dynamic models are statistical downscaling models. These often use empirical rules of thumb combined with high-resolution data for ground elevation and land use. Although simple, they can still add a lot of detail for a fraction of the cost of most dynamic models. And there are two main ways we use weather models. They can be used to forecast the weather or to reconstruct long histories of weather. This is typically more accurate than forecasting, as global weather models are able to assimilate historical weather records. In our experience, utilities often have a great handle on weather forecasting, but can overlook the benefits of information available in historical weather data. If we want to use weather model data instead of measured weather data, we need to be confident that it's accurate enough for our application. And so we always recommend a verification of weather model data in any project that uses it. So weather models, it can provide a large number of weather variables. Some examples that are particularly relevant to power system assets are wind speed, temperature, solar radiance, and precipitation. So that's rain or snow. All of these variables can be validated against measured weather data to quantify their accuracy. That would be against tested weather station data. And there are publicly available data sets for global weather station data. An example over Canada can be seen in the map here. And for those of you, I think I can see some people from the US, there's a similar kind of weather station set down in the US. So this may also be supplemented by any measurement data a client may have. And note that since this data set has not been used for the creation of global weather models, they are very valid for an independent verification of weather models. Here we see two graphs of modeled air temperature against measured temperature from a meteorological mast. The graph on the left shows the scatter between real and modeled temperature for each hourly record individually. The graph on the right shows the distributions of temperature, so that's also known as climatology. Weather models are particularly good at predicting temperature, and you can see that the correlation and R squared of the hourly data is very good. The climatologies are also very similar, indicating that weather model data would provide a reliable picture of the long-term range and distribution of temperatures. This slide shows the same graph, but for wind speed. The modeled and measured climatologies for wind speed are still very similar, but the hourly records are less well captured by the model than for temperature. So this means that care must be taken when considering the accuracy of the model for a given hourly wind speed event. But the overall distribution of wind speed over the long term can be captured very well by the weather model. And so for many power system applications, the climatologies may be more important to get right than the actual individual events. For example, identifying areas of a network that are more exposed to adverse weather over the long term. So this is still quite effective for most applications. So we've discussed the ways that weather data can be produced, how weather modeling works, and how to ensure the accuracy of weather model data. So now I'll go through a few case studies for projects that have used weather model data to quantify the impact of the weather on power system assets. So in this section of the webinar, I will discuss two case studies. The first will be around asset health of overhead lines. So that would be kind of a condition assessment based on wind-induced wear and corrosion risk. And the second looks at thermal ratings and ground clearances of overhead lines. And then I will then briefly mention the analysis of extreme weather on overhead lines, power forecasting models, and analysis of peak demand and power flow modeling. Before I begin with the case studies, I would like to stress one point. The person on the street cares about the weather in a broad sense. So for example, will it be sunny today? Do I need an umbrella? Utilities tend to care a lot more about the weather, about how weather impacts their business. So digital engineering are specialists in applying weather model data to power system applications. And so all of the following case studies use weather data to help understand the business impact of the weather, rather than figuring out whether it'll be sunny or rainy. So first, I will discuss an overhead line asset health project. I will outline the benefits of the project and then quickly step through the project and results. So because many utilities are struggling with overhead line assets approaching end of life, it's vital for asset managers to identify those assets or spans that are at greatest risk of defects and failures. If If certain lines are located in a very calm environment, perhaps they can last longer than expected. A primary cause of defects on overhead line assets tends to be the weather. The right combination of precipitation, humidity, wind direction, levels of chlorides and SO2 can be absolutely detrimental to overhead lines. And so in this case, we use the weather modeling techniques that I've explained in previous slides to identify those spans that are at higher risk than others. The primary benefit of this project was to extend the expected asset life of overhead lines. So extend that on paper. Although there were other benefits around inspection and maintenance practices as well. So overall, the estimated savings when deployed to the whole electricity network was tens of millions of dollars, seeing as the pilot on 15 routes saved our client in this case, so that's National Grid in the UK, it saved them £20 million. So that's more than 30 million Canadian dollars. And that was caused by a postponement of a complete re-conductoring project. So because of this, they were able to identify those spans that are in a much more mild environment, and they were able to extend the expected asset life. So before the project began, research and development was required to create models to estimate the exposure of overhead line assets. So this included 2 different vibration models and a corrosion model. All of the models considered the impact of historical weather as well as conductor specifications. The first was aeolian vibration, which is a very high frequency, low amplitude vibration, which can cause long-term damage to overhead line conductors and fittings. Levels of atmospheric turbulence combined with certain wind conditions lead to aeolian vibration. Conductor galloping is a visually dramatic type of oscillation that is often caused by ice forming on conductors. So these really high amplitude waves can cause instantaneous failures of assets. Corrosion is another cause of long-term damage to overhead lines. Corrosion rates increase in warm and wet conditions, and then are further accelerated by the presence of pollution or proximity to the coast. And then all 3 models were verified with data from the customer and other available data. So first we ran the models. First we developed the models, we created them, we ran them, and we presented them. And then we verified them with data from the customer. And it's good standard practice to also verify the raw weather model data used for the project against the verified weather stations in the region. So because if you're working particularly in countries such as Canada, US, UK, Australia, it's very easy to find several accurate weather stations in the area. And so it's very good to verify your data with that. So now I'll walk through the main project steps. So first, we ran the 2 vibration models at every overhead line span in the project. The aeolian vibration and galloping models used long histories of weather data as inputs. We continued by running the corrosion models at each overhead line span. This model also used very long histories of weather data and levels of pollutants as well as salinity. So crucially, the model also considered how levels of pollution have changed over the years. That also has a big effect on your assets. The map on the right highlights how urban and industrial areas, as well as transport networks, dramatically increase pollution levels. The calculated corrosion rate is affected by the weather, with corrosion increasing in warm, wet environments. And the weather can also transport pollutants onto power system assets. So all of this was taken into consideration. So once the levels of wind-induced wear and corrosion had been estimated for the network and presented to the client, we combined defect records from the client with these estimates to verify the results of the vibration and corrosion models, and to further refine these models. So it makes the models more kind of tailored to the client. The project resulted in asset health data sets that are usable by the client. So this means geo-referenced asset health data at every overhead line asset. So the map on the right provides kind of a flavor of asset health data, although it obviously has been simplified, desensitized, and randomized in order to protect our clients. The second case study was line rating and clearances. So I'll be discussing a project concerning kind of overhead line thermal rating and ground clearances. And again, I will go through the background and benefits of the project, the development required in advance, and then walk through the project step by step. So the capacity of overhead line networks is limited by the thermal ratings of conductors. These ratings are in place to protect assets and for safety reasons to prevent ground clearance limits being broken. So there are minimum distances between the ground and the conductor so that there aren't any kind of accidents happening in between. The operating temperature of a conductor is affected by, of course, the load being transferred by a circuit, the weather, with wind cooling the conductor and high temperatures and sunshine warming them up, and also the thermal properties of a conductor. So as conductors get hotter, ground clearances reduce due to conductor sag. So all of that needs to be taken into consideration by power system kind of asset managers and planners. Being able to transfer more load around an electricity network may allow operators to defer upgrades, may allow operators to actually connect new renewable generation sources, or even to reroute electricity during an emergency situation when the line is down. So if existing assumptions about the weather can be proved to be conservative, network capacity can be increased with no impact on asset health or ground clearance limits. And validated weather model data may be used to justify these decisions. At the start of this project, we again needed to carry out some research and development. So this was kind of the first time that we did this project. It was upon request of National Grid in the UK, and it was done through the National Innovation Allowance provided by the United Kingdom. So first of all, we implemented calculations for operating temperatures of the overhead line conductors. So these required weather data and conductor properties as inputs. Next, we implemented calculations for conductor sag, and these required operating temperatures from the previous models as inputs. And then we verified the models, so both in terms of the raw weather model data, as well as the outputs of the operating temperature and sag models. So to run through the rest of the project, first we calculated operating temperatures at every overhead line span. We used long histories of weather data to do this, and a snapshot of operating temperature time series is shown in the plot over here, or the graph. I started speaking like the British do, ever since I started working with in the UK. So next, we calculated different probabilities of exceedance for these operating temperatures. As an example, this gives the client an indication of the temperatures that are likely to be exceeded 1% of the time, 5% of the time, or 0.5% of the time. So different probability of exceedance temperatures are also indicated here, and then we can also calculate those. But three that were requested were here. So that's 1% probability of exceedance means that it's 1 in 100 operating temperature events. So the first output of the project was static ratings for overhead line circuits throughout a network. So these were calculated based on operating temperatures at each span within a circuit. So the example on the right demonstrates, once again, desensitized and randomized results in a map. So the client was able to identify all the different locations that would be the problem areas. And then they were able to, by looking at all of these different locations and different span results, they were able to make decisions whether to uprate a line or a route, or whether to keep it safe in case there's an emergency situation, or to identify locations where larger scale renewable generation can be installed. The second output of the project was ground clearances for every span in the network. So ground clearances were calculated by combining conductor sag, calculated using the operating temperature outputs that we got in the previous section, as well as the physical configuration of the network. So it was important to actually look at how the ground was structured. So whether something was on a mountain, a hill, whether there were smaller hills in between. It was quite a complicated project, but it was very interesting. So I just wanted to go over some conclusions from this project. Simulated weather can help develop probabilistic thermal ratings and ground clearances. And the fact that we have long histories of weather, model data allows for much deeper dive analysis into these issues. So for example, could static ratings definitions be refined? Could weather model data enable monthly ratings rather than seasonal ones? So there's a lot to consider. And before I finish off, there are other weather-related applications that can also help with the management of power system assets that I will briefly outline in the following slides. So first is our extreme weather analysis. It looks at historical weather data to identify towers more at risk of extreme weather. So this can be used during the planning moments of a new line in order to make sure that the newly erected assets can withstand the extreme weather that is possible in the particular area. And very highly detailed weather data must be used for this particular application because you need to make sure that you're getting the data for the right height of conductor and that you're catching wind tunnels caused by mountains, hills, that you're taking into consideration open areas, or sections that get a lot of sun, sections that get a little bit less sun. So this is a project that is very useful. So on this image here, you can see tower by tower, which towers might need to be strengthened in order to withstand, or may need to be overbuilt as opposed to the regular standards in order to withstand the weather conditions that they may experience in that particular area that they're being erected. And for some regions in the world, if you are able to justify underbuilding a particular tower, you are able to do so. So for some clients, we were able to identify those locations that they needed to spend the extra money, but then we also are able to identify by the use of weather models sections of line where you can get those savings. We currently provide to Bloomberg countrywide power forecasts for wind and solar generation. So we can forecast the output for individual wind and solar farms. And these forecasts are used, use historical production data for the country or farm, as well as weather data from large organizations such as the European Center for Medium Range Weather Forecasts. And these forecasts can be delivered multiple times per day, up to 2 weeks ahead. And so these forecasts are important for system operators as well as energy traders. For the demand analytics service, we combine weather data with our demand models. So this can be used to forecast electricity demand, or it can be used to separate the effects of weather from underlying changes in consumer demand behavior. So this improves investment decisions about which transformers require the most urgent upgrades to cope with demand, or which customers or which regions might be kind of using a lot more of their own distributed generation sources. So it gives you an idea of your system. And then different demand models are used to capture the different behavior of residential, commercial, and industrial customers as well. And we can also consider the impact of weather-dependent distributed generation, as I mentioned. And the final one is our power flow modeling. So supply and demand in the electricity system is weather dependent to different degrees. So we have created an electricity power flow modeling approach that uses historical weather data as inputs to capture the impact of weather on electricity system congestion and constraints. The map on the right here shows the model correctly capturing a weather event that resulted in significant wind power being transferred from Scotland down to England, resulting in constraint payments being made. And so this kind of modeling approach allows operators to assess the impact of different weather patterns on their network and to run scenario modeling to assess how future system upgrades can affect power flows. So in conclusion, we've discussed that weather is a key factor in managing power system assets. We've also outlined that weather models can be used as an alternative to installing weather stations. And we've discussed that weather models can be accurate and that this data is useful for many power system applications. So I will try to answer some of your questions if you may have some. I didn't realize how fast I went through that presentation. So, and if anybody is uncomfortable asking questions, feel free to email me. I can respond to those questions as well. I can also not include your name in these questions. I can include them on the summary or we can include them in the summary of the webinar without your name, if you prefer that way. So are there any questions?
Awesome. Thank you, Alex. This was a really interesting presentation. I learned personally a lot, and it was a very informative and nice to follow presentation.